physics video. I just thought I'd go over it one more time, the black and red part especially. Try to come up with a schematic, some kind of drawing. So, just to improve understanding. So let's start off with the idea that there's a field of energy. So it's not unlike this field of a light that's around me right now. It's a bunch of photons in this room. But only a certain number of the photons will hit me as an entity. And certainly only a very few number of the total will go inside my eye, will hit the eyeball in the right angle. Obviously it can't hit it from behind. So it'd be much better if I could just take my little eyeball out and put it here in space, and then you could get the idea that the light will come from all angles of the room, and kind of like the opposite of a light bulb. And so that's the universe everything is in. So it's like the opposite of a light bulb in the sense that the energy is constantly coming from all directions, and that's how the naked universe starts, the simplest. And what I'm arguing is that two things that are a manifestation of the universe's function, protons and electrons, two nuclear parts that can survive outside of an atom structure, and the neutron also, but we don't need to talk about that right now. The two opposite parts, the parts with the most interesting function, let's just say, for the purpose of the universe, are the proton and the electron, as they create the positive and negative electrical forces, magnetism. That is the real mechanism that bonds everything material together. It's what makes it matter that there's light in the room. The light couldn't do anything except go right through everything if it wasn't for protons and electrons. So the universe, all this light in the room here, for example, would be incidental. It would be nothing without something that can be affected by it. Change can happen. Without that, it just passes and it doesn't evolve into anything. It just goes about its business and it bangs into each other, and it just all doesn't make any difference. So, alright, so I'm going to talk about the proton and the electron. I'm going to talk about the fact that there's two elements of photons, two kinds, you could say, two colors, two whatever you want to say, out of, say, 100, that are the only ones that do anything, in the sense that they're the only ones affecting either protons or electrons. So I'm just going to make them red and black for the purpose of this example. And so the only photons that are relevant are the ones that can be affected, in the sense that they do something different. Something, the product is different than would be just going through each other, just passing in a kinetic way and interacting. Alright, so I've gone through this before, but it's this simple, really. So there's two kinds of fundamental interactions, perpendicular and head-on. And you can sort of see that the thing that changes is that when the things bang into each other, the polarization goes perpendicular, and in a sense that means the momentum goes perpendicular. But as you can see, there's momentum in both directions. It's just that the color changes, so the polarization changes. So the momentum is essentially changed in its direction if something is filtering for just that one polarization. So if all you could see were green photons, and green photons got disturbed by red photons, you'd see that there was a whole bunch of action, because all the green photons wouldn't be doing this consistent thing, they'd be doing an inconsistent thing. But anyway, and so then the head-on collision has the same effect, in the sense that the polarization goes in one way and it leaves the exact opposite way. That's the reflection. So this accounts for the fact that EMF, or magnetic and electric radiations, always leave the bodies that produce them, charged particles, perpendicularly. And this is called perpendicular. This little right angle means it's perpendicular. Anyway, and so the key thing is that you have these interactions. So this I could reverse, and I could just put the red arrow over here and the black arrow over here, and you see that's the inverse. So I could have them coming down this way, and that's the inverse. Or I could do it in the third dimension where they're coming in and out of the paper, and you can see it's all the same thing. But there's no inverse for the head-on collision, because that would require a black arrow to hit a red arrow. And the point is all these bits are moving the speed of light. So obviously nothing can ever gain on something else. Can't chase it, really. There's no chasing. There's no catching up. There's no plowing into the back end of something. So there's no rear end collisions. And that's another key important thing that allows there to be a difference in the universe, is that head-on collisions can happen, but the opposite of that can't. So that's just another key thing to keep in mind, is that there's reflection, but there's no real such thing as collection, if I could say it that way. Alright, so for the purposes of this schematic, call the black the electron. So we'll just say that's the electron. The rule is the black thing, okay, is only affected by red. So only things that are red coming in can do this perpendicular thing, or this head-on thing. No other color can do that. If it's red on red, obviously you wouldn't be able to see any difference. And the other colors are irrelevant. They can't change anything. They just go right through, theoretically. Whatever way, if this was a green, the green would go this way and the red would go this way, so you wouldn't be able to see the interaction. It would be invisible. Likewise, if this was green, it would just go straight through green, and the red would continue red, and you wouldn't be able to see the interaction. So so the electron is affected, okay, by red arrows. It holds black arrows, so to speak. That's what it's, the polarization that's relevant to its form, so to speak. And it emits the red. Yeah, like I said, I have to be careful. So, you know, because I keep switching these, and it's, you know, so my own brain is a little bit slow on the pickup on some of this stuff. I mean, just making the separations and being clear about them. Alright, so if I just put an electron in empty space, let's understand that the electron is made of, let's say I'm using black, so let's just keep this consistent. It's made of bits that are trapped in position. So you could call it orbits, whatever you want to call it, but they're trapped. And when the bits, the total fish, let's say it's a school of fish, if the school of fish isn't moving, you can sort of understand that there has to be as many fish going this way as this way, and that way as that way, and this way as that way. So in the 3 dimensions, this body would be in a not moving position. It wouldn't be moving its position substantially. At once, as it, in the sense it has no velocity, it has no imbalance, so everything's balanced, so there's nothing motivating it, so to speak, nothing pushing or pulling. Certainly I will argue in these videos that there is no pull, but there's nothing compelling it to move in one direction. But it is going to move, and so let's apply the rules of the natural force. Would be that, okay, so it's being hit from all directions in a clean universe. It gets hit from all directions by red arrows, and in a clean universe, theoretically, it would be equal amounts from all sides. So you can see that over time, what's going to take place is there's 2 kinds of interactions that can happen from any angle. The head-on collision and the perpendicular. So if this arrow hits this one, it'll head-on collision. If it hits this one, it'll do the perpendicular thing. So basically there's only two possibilities of an outcome. This arrow comes in and the switch is that the redness goes this way and the blackness goes now down. So then it would have extra down arrows. So you can sort of see if it hit this one from up here, this black would end up going down, the red would end up leaving perpendicularly, and you'd end up with now you have an imbalance. You'll have two arrows going down and no arrow going this way, and that's going to cause this thing to probably move that way. Should have done that in black. Yeah, right. Yeah, keep the emission forces different than the reflected forces, so to speak. And so you would have the, in a sense, you would have a movement. But then you'd know logically that this arrow is going to do the same thing over time. And so over time, what this thing is going to do is basically jitter. It's going to move this way, then 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 this way. And it's going to do that also in the other dimensions, the same kind of movement. But it really won't go anywhere. So it's, when I said movement, I'm talking about in its place, so to speak. It'll go up, it'll go down, it'll go over, it'll go over. But in the end, it's all going to end up being in a small circle of what the possible range of its movement due to the erratic, random occurrence of this pressure. But the pressure is not going to take it outside of a realm of wobble, and that you could almost call Brownian motion. If you know anything about the history of atoms and particles, it was discovered that atoms and little bits are moving all the time. They're just not going anywhere. They're vibrating. And that's I would argue this is the cause of that motion, is just the fact that even in a perfectly random and perfectly balanced force field, there's always going to be moments of imbalance. But they're just moments. And they're always compensated for. Okay, so now let's use the example. Well, just to point out, to be clear, the reds do come in from, and hit the head-on collision, and the red goes back the same way it came. And the reaction that can't happen is this red can't hit this black in the rear end and create a reflection the other way. So one end reflects, the other end can't do the reflection thing, but again, it can do the head-on collision thing. So now all you're really looking for is things that create an imbalance. And once there exists an imbalance, what's the consequence of that? So let's take this electron, and we'll just represent with one arrow that it has an imbalance in one direction. So now it's moving a velocity. And you can sort of understand that the speed of this velocity will be based on how many little bits, little arrows are in here. So if it has, let's just for the sake of simplicity, say it has 1,000 arrows. If it's only one of the arrows extra in this direction, that means so it would have 501 going this way and 499 going that way. You have to do to figure out its speed, it would be a percentage of the speed of light, and that percentage would be based on the ratio of that 1 to the 500. So it would be like 1 over 500 equals proportionally the speed of light over 1. And that proportion would be related to what percentage of the speed of light, 1/500th presumably, the body would be moving. So obviously the density of not obviously, but one would argue, the density of an electron might be in a billion of these arrows. So you can sort of understand that 1/billionth of the speed of light would start getting into the range of something moving a foot a second or something like that. A velocity we're more familiar with. rather than the extremely fast velocities of the speed of light. So the real momentum that a photon can impose on, say, and we're calling it a photon. One of these arrows would be like a photon. They're gravitons, or they're magnetons, or they're quantons, whatever you want to call them. But the idea is they have a momentum. The momentum is going to be converted in the sense their polarization will be left, and their direction will leave perpendicularly or reflect their original direction. And they'll move the thing by essentially giving it a different fish. So one of its fish will be killed in the school, and I'll replace it with a fish going the way the photon was going. So you can sort of look at it that way, that what happens when an imbalance in energy goes into the school of fish, essentially what's happening is you kill one of the fish that's in the school that's going the wrong way. Can't be one of the fish going the right way. It has to be one of the fish going the wrong way. The 3 wrong ways, or the 5 wrong ways, if you're going to count all 3 dimensions. It kills one of those fish and replaces it with a fish going that way. And the photon's doing essentially the same thing when it hits an electron. The first part of the photon, the front, the photon is basically 2 tons. But the ton would enter the electron, give it acceleration, in the sense that now it's killed one of its fish, it's replaced it with a fish going the way the photon was going, and now that speed will be spread over the entire school of fish. So it has to be, in a sense, all the fish have to be, for a while, they have to go the direction that that fish is going. So that fish's speed, of the speed of light, is essentially slowed down by being dampened by all the other fish's movement. And then, but that in the end, it'll tell you through all that wobbling and bouncing, in the end there'll be an actual roll speed, so to speak, that's incurred because of this extra bit of momentum you've put in, and it's spread over all those fish. And so you turn a speed that's 160,000 miles a second into a speed that might be 500 feet a second. Alright. Yeah, that's enough of that. Alright, so I have an electron that now has 1 extra fish, or 2, whatever. It has a little bit of a velocity, okay, in one direction. And the consequence of that is, of that extra arrow is that now there's the external world is still the same, let's say. We're going to put another body in here eventually. So it still has this balance of the same number of arrows in it. But the trick is, the pressure arrows, you're going to be hitting more of these, okay, the ones forward, than you were before. It's just inevitable. And if you recognize the fact that you're now, let's see how to put this, because you're moving into this energy, but at the same time you're moving away from this energy, so you're going to be getting less impacts from this side, in the sense that you'll do less of these tangential things. Those are your only choices, going this way and also hitting the fish that are still going the wrong way. So you have less fish going that way, and you still have fish going all these other directions. So I don't know exactly how to. So you still have all the other stuff going on, you just have a little extra going this way. But there's a consequence to that in terms of what possible reactions can take place is going to be changed based on that change. So you can sort of understand that, in a sense, these arrows coming down here are more likely, right, to have an interaction with an arrow going that way than they are to have an interaction with an arrow going that way. So you can sort of understand that there's going to be a little bit more interactions with these arrows, which means that you'll have more, a slightly tiny bit more, okay. The consequence overall will be that you'll have a little bit more that leave this way, in terms of what's inside of here, then we'll leave this way. So this will be the bigger, a little bit more will as a consequence of the interaction, more will go this way than will be going that way. And another consequence is you're going to hit more, you're going to have more head-on collisions. You can't catch up to the, there's no other choice in a sense here. There's head-on collisions, and then there's reactions with these perpendiculars. But we know these two sides, this going this way doesn't have any inequity. So you know you're going to have just as many that'll hit ones going this way as that way, so nothing will change in the up and down sense. Yes, it's still going to do the random thing of up and down, but there's not going to be any imbalance in a direction. But you do know that there's going to be more of these head-on collisions, and the head-on collisions are again complete reflections, so you're going to have all of those arrows are going to come right back. So everything you hit is going to come right back as a reflection. So you have essentially two sources of extra red arrows, and those how to say that, this one you can't really count. Okay, so I will say that these extra coming from the perpendicular direction, the catch to that is okay, the catch is that they are moving out in past this interaction field, so the perpendicular interactions are less likely to occur. And what's the other factor? Okay, so that's, I'll have to put a question mark there because I haven't finished that one. But anyway, the one important thing to understand is that the faster you go into the field, you'll just create more reflections. So you can't avoid the fact that you're going to produce exactly what you get from the red side from this direction. The only other choice is the tangential, and over time, the faster you're going, that dimension is going to disappear altogether anyway. But it doesn't really have anything to do with the equation, because it's still not going to be any more than the regular amount of those interactions. I mean, there's still going to be balance going this way and this way. And so you're not going to gain anything that you can apply to a direction. And you're certainly going to have less going out this way just because of the imbalance you started with. Okay, well that isn't... I mean, it's okay. I'm explaining it, but I guess I wanted it to be a little bit harder an explanation, just so you can get the idea of why, when two things are moving into each other, they're going to end up absorbing each other's radiation, and that radiation is going to move them in the opposite direction. So that's what we'll do now. We'll just take the two things. So these are two electrons, and they both have... They don't really both have to have a velocity towards each other, but let's just say they have a velocity towards each other. By this reflection rule alone, you can sort of understand that they're going to be, in a sense, producing red arrows. Anything that comes at them, they're going to reflect. So as these two bodies came from the open field, you could understand that they're reflecting the red arrows in front of them. And as these two bodies start to affect each other in the sense that they start shielding each other, shadowing each other from what you could understand to be access to the external world. So in between these two bodies isn't going to be the same as what's outside of them in terms of what's coming in, and you sort of can understand that. But I'm just saying, coming into it, you can understand that when it did have velocity, it was producing a little bit more arrows in front of it. And you can understand that if the red arrows, this one's shooting red arrows, and they're most likely going to get reflected back, and the same thing happens to these reflections, you can understand that this becomes very dense in red arrows. Really dense. And that those red arrows will hit, it'll be, the more of them there are, the more of them that will kill these perpendicular directions. So you can sort of understand that what they're going to do, you know, to get consumed, the only way they get consumed by these two bodies is they have to do a perpendicular reaction and leave as an EMF in the perpendicular direction. So that's the only way they can be disposed of, in a sense. So the more of them you have, the more likely you're going to have interactions perpendicularly, and the more force you're going to have to release sideways, and in a sense you're going to be absorbing the momentum. So you say this arrow goes into this one, you can see that it's going to kill its velocity going this way because it's going to add an arrow going this way. So it's going to kill one of the fish going the wrong way, replace it with a fish going the way it wants, and it will, you know, produce you know, the arrow going perpendicular, the EMF, the electrical or magnetic force, and now it's becoming balanced. So it's going to lose its velocity this way, and it's going to start moving that way, and it's going to be producing field energy, red, into the field. But that's the nature of the repulsion, and so I just wanted to clarify that, because I don't think I've explained it well enough. And I don't think this is complete enough either. But I think the key point that I just wanted to emphasize is that this is the difference that makes the difference. You can't have the rear end collision, and you can only have the head-on collision, and the head-on collision is a reflection. And it's that reflection that magnifies the consequence of your velocity in terms of the fact that you're going to produce field energy, more field energy in front of you than perpendicularly to your velocity, and that little bit more is going to be enough to convert anything you interact with that is similarly sensitive. And you can sort of understand that if this was a proton, it's doing exactly the opposite thing, and so it's going to be affected by this energy exactly the opposite way, in the sense it's not even going to see these red arrows, and it's going to still have all the pressure from the external world pushing on it. So it's going to be attracted rather than repulsed. Alright, that's probably enough. So the important thing is understanding that there's no rear end collision, and that these things do not travel in straight lines ever. So I would argue that a proton or an electron can never have a straight line velocity. They're always going to have irregularities in the field energy, so they're always going to travel some kind of line that will average into a straight line, but it won't be a straight line. And so they'll never go the speed of light for that reason alone, not in any kind of form. But they can't go the speed of light anyway, just because they exist as multi-dimensional objects. Like something like a muon might be a two-dimensional proton. It's these manifestations of these things. But so you're talking about 3 dimensions, and you know, you can try to come up with ways to draw that aren't totally awful. But so there's no way it can move the speed of light, because these other dimensions would always be slowing it down in the sense that they got arrows going the wrong way. And you can't go the speed of light if you have any elements going any other direction. All your fish have to be going the same way for the school to go as fast as a fish. So you can sort of understand that if I have a fish, and I have a school of fish, and they all go the same speed, the fish, you can understand that the only way the school of fish can go as fast as the single fish is they all have to be going the same way as the single fish. Alright, I think that's enough. What can also be an illusion of speed is the fact that electrons and protons may not be able to travel the speed of light, but they can push each other. Okay, I mean, this one can push with force into this one at the speed of light. So if you just go by the field pressure between them, if you count this pressure as an entity, this can flex at the speed of light. So you can move electrons a little bit at the speed of light, but you can't move them from position to position faster or at the speed of light. It's much slower to move one than it is to vibrate one or to push one, and then it pushes the one next to it and it pushes the one next to it. The pushing thing can happen very fast. The actual moving of it can't. There's probably ways to illustrate that, but maybe there's like a water example or something. I'm just trying to think of the movement of a drop of water versus the movement of a wave. The wave might move much faster than the actual droplet can move with the same amount of energy. But that's the problem, is that one's really energy dependent. But I think you can get the point that you can vibrate, you can wobble something quicker than you might be able to push it or move it. But anyway, I think that I did what I wanted to do here, which was just explain how you have this repulsive force, and that the repulsion is really just made out of the fact that you become very reflective as you move towards something. One of the two bodies, for two bodies to interact, one of them has to have a positive velocity towards the other. And that positive velocity is essentially a reflective velocity. And it's that reflection that will, in the end, create the repulsion. So yeah, it's if you thought of it as you become a mirrored surface, and then whatever you're heading towards, you end up looking like them, and then they say, "Ooh, what the hell's that?" You know. So yeah, mirrors often don't do that to you, right? Oh my God, and you move away. Same kind of effect, except metaphorically quite different. So anyway, yeah, that's it. I'll try to do this again. I just have to keep working at it a little bit. I'm just trying to get to the basic elements, and I'm saying these elements are all you need. This theme, okay, it's all right there, and this tiny bit of information is all that's really needed to understand most of the electrodynamics, as it's called, of nuclear parts and the field energy. And that's gravity, and again, magnetism. I'll just say briefly, the whole point of why I'm making this point is this red and black thing. Is that what magnetism does is it creates filters that enable all of the energy to be converted into whatever the particle is. So any color that comes through will end up coming out red. And so it turns the entire field energy into this polarized, identifiable, the stuff that's going to affect other electrons or other protons. So it magnifies the effect by converting field energy into relevant energy, in that relevant to the electron and the proton. Alright, that should be enough. Till next time, when I'll cut this even a little finer and get a little more precise. Like I said, the one element it's kind of obvious that if I have a velocity going this way, I have more fish going this way, that these interactions are going to more likely produce forward result because of the rule. So I just have to figure out what counterbalances that. In terms of what we do note is that you don't lose any forward velocity from perpendicular interactions. So moving sideways doesn't affect your forward velocity in this circumstance. It doesn't stop you from moving over time. You maintain that in the end, and that has more to do though with the fact that the rest of the field is still pushing. There's still a balance between these two sides. You're just reflecting one side of the balance, so you're still getting hit by an equal number from both sides. So your default original condition will be maintained in the end. So in a sense, velocity is a disturbance in a direction that will, you just can't get rid of that. You can't get rid of the imbalance until the field corrects it. There has to be an imbalance ahead of you in the field to fix the imbalance in you, because otherwise you're actually still wobbling in the direction of your velocity. I mean, you know, the tendency is the direction. At any one moment, you don't have to have it, but you will have it inevitably because of the imbalance exists, and there has to be a counterbalance from the field. There can't be just you can't randomly get rid of it. You have to get rid of it because of a non-random event. A true counterbalance. That's it. So until the counterbalance shows up, you will remain imbalanced. Okay. Well, I'm going to post this video even though I'm not totally satisfied with it. But anyway, till next time.